All right, so this is chapter P1 of the book, the preliminary chapters. So we're going to go through the Pythagorean theorem and some of its consequences and some details about how to deal with some computations. But before we begin that, let's get down some basic notation and terminology. So here we have the plane, x and y, so this is the plane. If we mark these coordinates, right, let's say 1, 2, 3, 4 for each of these, then if we look at, for example, this point right here, this guy is 3 steps in the x direction, 2 steps in the y direction, so we denote this point by 3, 2, and we can do this for any point in the plane. This guy right here is 1 step to the left and 3 steps down, so it's -1, -2. 3 steps down, so -3. Okay, and for example, this point right here would be -1, 2. All right. So again, just some preliminary notational business. So this first area here, we call that the first quadrant. So usually we label these with Roman numerals. The second area here, we call it quadrant 2. So we go counterclockwise as we go around. The third area here is quadrant number 3. And down here is quadrant 4. Okay, this kind of coordinate system is called Cartesian coordinates. And it's, for our class, it's going to be one of the primary ways to locate points in the plane, right? So if I say I'm working with the point at 4, 7, you know exactly where that is. All right, an alternate name for this is rectangular coordinates. In the future, we'll talk about different coordinate systems, which are useful in different contexts. If you're working with a lot with circles and rotation, then sometimes or often polar coordinates would be more useful. We'll see that towards the end of the class, actually. Okay, so let's start with our kind of core theorem, which is the Pythagorean theorem. And what we're going to do in this class is we're going to have a lot of formulas, we're going to have a lot of properties and theorems, and pretty much all of them eventually can be traced back to the Pythagorean theorem. We're pretty much going to justify every formula we see in this class, or justify every algorithm, justify every theorem. And again, pretty much all of them can be boiled down to all the way down at the bottom to the Pythagorean theorem. So what does that say? If we have a right triangle, so right triangle meaning that it has a one angle of 90 degrees, then if C is the length of the hypotenuse and A and B are the other two lengths, it doesn't matter the labeling for the other two. C is the important one. And the hypotenuse, of course, being the side that's opposite of the right angle. All right. So if C is the hypotenuse, then I guess mostly written as A squared plus B squared has to be equal to C squared. All right. Okay. This is only true for right triangles. If you just have a random triangle, so if I just draw a triangle like this, that's not a right triangle, so there is no angle here of 90 degrees, then this is absolutely not true. So A, B, and C they do have a relationship, but it's far more complicated. Not as simple as A squared plus B squared equals C squared. We will actually talk about their relationships later on in the class. And one way to think of that relationship is that it's an extension of the Pythagorean theorem for triangles that are not right triangles. All right, but for now, make sure you remember that the Pythagorean theorem is only true for right triangles. Never try to use it for a situation where you don't have a right triangle. All right, so in terms of computations and applications, one thing that we will see quite often in this class is where we have a right triangle and we know two of the side lengths. So for example, 10 here and 4 here. And we would like to know what this last length is. So the Pythagorean theorem gives us exactly that, because it says that the sum of the squares of the sides, right, of the two non-hypotenuse sides has to be the hypotenuse. So this question mark squared, whatever that is, plus 4 squared has to be equal to 10 squared. All right, so that tells me question mark squared is equal to plus 16 is equal to 100, which tells me question mark squared is equal to 100 minus 16, which is 84. By the way, when I use this symbol here, this means is equivalent to. So what I mean by that is that, and we'll use this a lot, this equation here, for example, this first equation here, is equivalent to the second equation. What that means is if I solve the second equation, then the same solution will work for the first equation. Or if I solve the first equation, the same solution will work for the second equation. All right. So as mathematical problems, they're the same in terms of solutions. All right. And of course, the second equation is equivalent to the third equation. And so solving the third equation is the same as solving the second equation, is the same as solving the first equation, which is ultimately the equation we want. All right. And in math, what we always want to do pretty much is start with a problem that's kind of difficult. And as we go down with these equivalences, our problem hopefully gets easier and easier and easier. All right. And you can see our third equation here is easier than the first one in that we actually almost have the answer, right? Question mark squared is equal to 84. Okay. All right. So in fact, let me actually do the next step. This tells me question mark is equal to, and here's the thing that I want to emphasize in this class because people always forget this. Whenever you take square root of both sides of an equation, you have to pop out a plus or minus. All right, so I'm going to take the square root of both sides because I see a question mark squared here. And if I take square root of both sides, then that clears that square, right? But when I do that, that means I need to pop out a plus or minus. Okay, and the reasoning for this is, or a good way to think of the reasoning for this is that when you have something squared equal to a number, right? Let's say, let's do a simple one. Let's say x squared is equal to 4, right? Well, x is equal to 2, right? But x can also be minus 2 because when you square the minus 2, the minus sign goes away, right? So whatever number you find whose square is something that you want, negative of that number will always also work. Okay, so here our answer is going to be square root 84, but negative of that will also always work. All right, so in short, whenever you square root both sides of an equation, you've got to pop out a plus or minus because there's always going to be two solutions. All right, as long as there are solutions, of course. Okay, now I emphasize this, but in this particular example, we don't want the negative one because we're talking about the side of a triangle. And the side of a triangle can't have negative length, right? A triangle can't have negative length. So in our particular situation here, this tells me that question mark is equal to positive square root 84. All right. So even though in this situation, you would technically have been correct if you forgot the minus sign, there will be many, many situations in this class where if you forget that minus sign, you're gonna miss important solutions to your problem. All right. Okay, so that's one example of using the Pythagorean theorem to get information about your triangle. All right. Now, one thing we see here is that we pop out a square root. And so it's kind of believable for this class that we're going to be working with square roots quite a lot. right? When you have the Pythagorean theorem, that means you have a lot of squares. And if you're doing some algebra like we did here, right, dealing with squares, that means you're very frequently going to be taking square roots of things. And when you take square roots of things, right, that means you're going to have to be dealing with square roots. And so one thing we absolutely need to be comfortable with is actually manipulating square roots and manipulating quantities within square roots. Okay, so our next mini section here is how to work with square roots. All right, so just the rules of what is allowed and what is not allowed. Okay, so in short, never move anything in or out of a square root unless you have a rule or you're absolutely sure you're allowed to. Okay, this is actually a general rule. Not only square roots, never move anything in or out of parentheses, never move anything in or out of quotients unless you're absolutely sure you're allowed to. All right, so always stop and think for at least 1 second to see whether what you're doing is legal or illegal. Okay. What I mean by this is, for example, if I write square root 4 plus 9, right? A lot of people immediately will be tempted to say this is equal to square root 4 plus square root 9, right? And the temptation is there because you know square root 4 is equal to 2, and you know square root 9 is equal to 3, and so, presumably you would have the answer of 2 plus 3, which is 5. Okay, but this is not going to be correct. You're not allowed to do this step right here because there is no rule involving square roots that allows you to split a square root when you're talking about sums. All right, so you're not allowed to do square root of a plus b is equal to square root of a plus square root of b. Absolutely not true. And in fact, you can see that it's not true in this particular example, right? The left-hand side is actually equal to square root of, if I just literally add 4 plus 9 is square root 13. Okay, but square root 13 is definitely not equal to 5. And how do I know that? Well, if I square both sides, right, I would get 13 on the left and I would get 25 on the right. And 25 for sure is not equal to 13. Okay, so this step here is definitely not allowed. All right. Same thing with subtraction. Square roots do not interact well with either addition or subtraction. Okay, and when I say you shouldn't do this anytime you have parentheses, it's going to be the same. I'm going to emphasize this very, very heavily when we talk about functions next week, or maybe the week after, that you cannot move things in or out. So we'll be talking about the sine function. We'll describe exactly what it is when we get there, but for now, I just want to emphasize when you do have a function like sine of x, sine of 3 plus 5 is definitely not equal to sine of 3 plus sine of 5. All right. Or maybe for a more pedestrian example, just with parentheses, 3 plus 5, whole thing squared, that is not equal to 3 squared plus 5 squared. All right. So you want to be very, very careful when interacting with parentheses or square roots or quotients, right? By quotients, I mean something like 4 over, let's say, 7 plus 9, right? Definitely not equal to 4 over 7 plus 4 over 9. Okay, so splitting things, whenever you do something like this, right? Splitting the square root into 2 square roots, splitting the sine into 2 sines, splitting the power into 2 powers, or splitting this quotient into 2 quotients, very possibly you're doing something wrong. Okay, and in fact, all of these examples here are completely wrong. Okay, and you can check it, right? 3 plus 5 is 8, 8 squared is 64. On the other hand, 3 squared is 9, 5 squared is 25, 9 plus 25 is 34, not equal to 64. All right. Okay, and the same thing with this last quotient here. So again, make sure you pause at least a little bit to see if the property that you're trying to use is true. Now, sometimes it might be true, right? So this quotient one, if I had 7 plus 9 over 4, that would be equal to 7 over 4 plus 9 over 4. That one's okay. All right. So make sure you know what is okay, what is not okay. And the default thought in your head should be that it's not okay. And you should always have to justify that it's okay if you want to use it. Okay. A lot of people will be making mistakes like these at this point in the class. One of the goals of the class is to make sure as quickly as possible you're not making these kind of mistakes. All right. They're very, very bad mistakes because immediately your whole problem is wrong once you've done something like this. All right. And they're very foundational kinds of mistakes that you really can't afford to be making. Okay, so we talked about what doesn't work with square roots, but there are some properties that do work with square roots. And in fact, square roots interact with multiplication and division very well. And that's essentially because square roots have something to do with multiplication, right? When you have a square root of a number, you're kind of talking about, it interacts, you're talking about multiplication, right? Square root of 7 is the number that when you multiply it to itself gets you 7, right? So square root has something to do with multiplication, and in a way that means it interacts well with multiplication. Okay, so for example, our answer upstairs was square root 84, and that's actually equal to 84 is equal to 4 times 21, right? Why did I want to write it like this? Well, because I want to see fours. I want to see squares under a square root. Why do I want to see squares? Because this next property is true. So this is equal to square root 4 times square root 21. So you're allowed to split square roots multiplication-wise, right? But definitely not addition in terms of addition. Okay, so this guy here, up here, absolutely false. But this guy down here, absolutely true. All right, square roots interact very, very well with multiplication. Okay, and here's the reason why I wanted to deal with the fours. It's because square root 4, I know, is going to be 2. All right, so this is 2 square root 21. All right. Okay, so one thing you want to do is make it a habit to, if you have a square root of a quantity, an integer quantity like this, to try to simplify it if you can, like I did here. There's a few reasons. One reason is just to get the practice. I think a lot of people haven't had enough practice with this because I think one of the major problems in math these days is that people start using calculators a bit too early. And so that causes them to not be able to compute as efficiently without a calculator. And while you think, who cares, right? As long as I have a calculator, it doesn't matter. It matters because while you do have a calculator for, problems like this one here with numbers, we're going to be moving into working with abstract quantities. And so it won't be just square roots of 84. We'll have square roots of, something like x to the 4th times x squared plus 4x minus 1, something like this, right? And if you were never comfortable working with square roots of numbers, it's going to be really hard for you to be comfortable working with square roots of complicated expressions, right? So for example, if you're very comfortable working with square roots of numbers, pulling out this 2 here, then it'll make you a lot more comfortable doing something like this, pulling out a x squared out of this expression that I have, right? Let me do this in 2 steps just to make it kind of more like what I had upstairs. So this is square root x to the 4th, x squared plus 4x minus 1, right? And so this is x squared 4x, x squared plus 4x minus 1. Okay. This is true for square roots, but this is especially true for working with fractions. I find that a lot of people, again, started using calculators too early when it comes to working with fractions, and so they're not comfortable with fractions. And so when they do compute with fractions, they make a lot of mistakes. And worse yet, when we start working with quotients of things which are not numbers, then they're especially uncomfortable. And in those cases, calculators can't help you, right? If you want to add, like up here, 7/4 plus 9/4, you could do it with a calculator, right? But, very soon we're going to be working with something like sine x over cosine x, right? And then expressions having to do with that. And if you were never comfortable with, just number fractions, it's going to be a really hard time for you when we get into kind of quotients with functions and having to manipulate those, which we will be doing quite a bit. All right. So work with fractions, work with square roots as much as you can. Do not use calculators as much as you can. Avoid calculators as much as you can. All right. Okay. By the way, when I say square root 4 is 2, upstairs I just said something about, when I square root both sides, I should pop out a plus or minus. There's no contradiction here. There's no problem in terms of what I said. When we, by kind of convention, if we write down the square root of a quantity, square root of 49, the answer should be positive. This symbol, when I see this symbol, square root of 49, this means this is equal to the positive number. This is literally the definition of this symbol, all right? Whose square is 49, all right? So the key is the positive, all right? So when I write square root 49, I mean 7, okay? That's why we had to put the plus or minus upstairs, up here, because when I write square root 84, I only mean the positive square root of 84. And so, because the answer could have been negative as well, I need to physically insert this minus sign right there. All right. Okay. So that's just a small note on the square root symbol. Okay. So square root interacts very well with multiplication or product. It also interacts very well with quotients. So if I had square root 44 over 27, that is equal to square root 44 over square root 27. So just like with multiplication, you can split this square root into two different square roots. All right, that's legal. Again, with addition, absolutely illegal. All right. Okay, why would I want to do that? Well, again, each of these guys are, again, our theme of math, that each of these guys now are individually easier to work with, right? Square root 44 and square root 47 and square root 27 individually are easier to work with than square root of the whole thing, 44 over 27. All right, and in fact, you can see this, right? 44, I can easily see, is 4 times 11. 27 is 3 times, let's say is 9 times 3, right? So 9 times 3. And so using my properties of the multiplication property, I know this is square root 4 times square root 11 over square root 9 times square root 3. And so this is equal to 2 root 11 over 3 root 3. Okay. So it makes it so that it's easier to manipulate and clean up my expressions. All right. Oftentimes you'll see this, that when you have a property or some object like the square root that interacts well with multiplication, it'll interact well with division as well. And that's because, in a way, division doesn't exist. In a way, the correct thing to think about when you have 44 divided by 27, that's just actually equal to 44 times 1 over 27, right? So things which are division can always be written in terms of multiplication. And so in a way, again, division is something that doesn't exist, right? Well, you might say that's BS because what you just have here, right, is 1 over 27. Isn't that division? Well, technically, in the most mathematical sense, 1 over 27 is not division. 1 over 27, this is the thing. So this is the number that, when multiplied with 27, gives you 1. Right? So this is actually the technical definition of 1 over something. So 1/3 is actually technically the number that when you multiply it to 3 gives you 1. All right. So a nice actually side note consequence of this is that, people often wonder, why is 1 over 0 not allowed, right? Why is this something that doesn't make sense? Well, if I go by this definition that I just talked about right here, right, 1 over 0 would be the number that, when multiplied with 0, gives you 1. Right? I'm just replacing, see this denominator here at 27, right? I'm replacing the 27 with a 0 here, and I'm replacing that 27 there with a 0 here. So literally the same, it's the same idea, okay? Now, if we think about this right-hand side, this quantity in quotes here on the right-hand side, what is the number that when you multiply it with 0 gives you 1? Well, one of the most important properties of 0 is that anything multiplied to 0 gives you 0. So there is no number that when you multiply it to 0 gives you 1, right? There is no such number. And so that's the actual reason why 1 over 0 is illegal. Okay? So there is no such number. Is no such number. And again, it's because there is no number because everything multiplied with 0 is 0, right? And so 1 over 0 is illegal. That's the actual real mathematical reason why you can't have 1 over 0. All right. Okay. Now we just talked about some interactions. We had square root 44 over 27 is equal to 2 root 11 over 3 root 3. So let me just copy that down. 44 over 27 is equal to 2 root 11 over 3 root 3. Oops, sorry. One thing that you possibly, well, almost certainly will have done in the past is when you see roots in the in a denominator, you've very frequently probably been asked to clear it, right? So a general idea is we don't like to have roots in denominators, roots of numbers in denominators, like this square root 3 down here. Okay, so if we do want to get rid of roots in a denominator, one thing you can always do is by multiplying that root on the top and the bottom, right? And this is perfectly legal because root 3 over root 3 is just 1. And so actually I haven't changed the expression, right? If you multiply 1 to something, it still stays that something, right? That's actually the most important property of 1, right? And so this guy, square root 44 over 27, let me put this in the second line, is equal to 2 root 11 over 3 root 3, and that is equal to 2 root 11 over 3 root 3 times root 3 over root 3. And then the reason for this root 3 is, so in the denominator, the root 3 times root 3 is just going to be 3, right? So this is just going to be 3 times 3. And then on top is going to be 2 root 11 times root 3. And if we clean everything up, this will look like 2 over 9, right? So 3 times 3 is 9. And then on top we have a root 33. Okay, so let me write it like this. And now we have no square roots in a denominator. Okay, it's just a nice clean 9. All right, so get into the habit of doing that as well. Now the question is why, right? Why were you asked to do this when you first learned square roots? And there is actually a good reason. The reason being that, well, let's say we each have a math problem, have the same math problem, right? Let's just take this one actually, to simplify this number here, square root 44 over 27. And your answer is 2 root 11 over 3 root 3. And my answer is 2 over 2 ninths root 33, right? Now, our answers are the same, right, as we've just seen, but it's not obvious, right? It's not obvious that they're actually equal. And this is kind of annoying, right? If you're, for example, if you're working with another student in the class and they get one answer to a problem and you get seemingly a different looking answer, right? It's kind of annoying that, you know, they actually might secretly be the same, but you didn't know it. So what happens when you clear the denominator of roots is that you're making it a convention to force everybody to have this, in a way, the same answer, right? So if I demand that everybody clears roots from denominators for this particular problem up here, then everyone's going to get the same answer, 2/9 with a root 33 on top, right? As opposed to something like this, where it's hard to tell who has the right answer, who has the wrong answer, whether the answers are the same or not. Okay, so we'll see this a lot. A very common one we'll see is 1 over root 2, right? That's equal to, well, let's clear it, right? 1 over root 2 is equal to 1 over root 2 times root 2 over root 2. Well, the denominator root 2 times root 2 is just 2, so that's root 2 over 2. Okay, so these two guys are actually the same. And again, you know, if you didn't do the convention of always transforming it to root 2 over 2, then you might not realize that, you know, you and someone else may have had the same answer. Okay. All right, so it's a kind of, think of it maybe as a standardization, right? If you're using kilometers and someone else is using miles, there's going to be a huge room for misinterpretation. So this is like getting everything into miles, or everybody's using kilometers. Okay, and this is actually the same reason why when you first learn fractions, you're kind of taught to always reduce the fractions, right? 4/6, you're always asked to convert that to 2/3, right? Because again, the standardization is good. It's easy to compare answers, or easily you can tell whether you're talking about the same quantity or not. Okay, let's talk about an application of the Pythagorean theorem. So let's draw our axis again. And let's think about 2 points. So here we're going to go a little abstract. So I'm going to call this point here x1, y1. And I'm going to call this point up here x2, y2. All right. And as we've talked about, the meaning of this is that this location right here along the x-axis, that position is x1. All right. And this height right there, that's y1. Okay. And in the same way, this position in terms of left and right is x2, and that height is y2. Okay. All right. So the question is, something that we'll want to kind of need to understand a lot is, what's the distance between these 2 points? Right? What's the length of this guy right here? Right? If I took out a ruler or something, right, what exactly is the length of this guy right here? Okay. So the question is, what is the distance between x1, y1 and x2, y2? All right. Okay. Now, so first of all, a supernatural question. It's a very natural question, right? You have a map. You have 2 points on your map, right? How far are those 2 points from each other? That's exactly this kind of question here. Okay. So where does the Pythagorean theorem come in? Well, whenever you have 2 points like this, we can create a right triangle just by filling in a horizontal line here and a vertical line there. And again, the most important feature here is that's a right triangle. Okay, because completely horizontal and completely vertical lines, they're perpendicular to each other, 90 degrees. All right. Okay, so how does that do anything for us? Well, we actually know the length of these 2 blue sides. So this first length here, the horizontal length, is going to be, well, x1 is here, x2 is here. So the distance between them is x2 minus x1. Right? Just imagine if x1 were 2 and x2 were 5, right? Then I would have 1 mark here, another mark here, 2, 3, 4, 5, right? What's the distance between them? 1, 2, 3, right? What is 3? It's exactly 5 minus 2. Okay, so this side length down here is exactly x2 minus x1. All right. Okay, same thing with the vertical, right? What's the length of this vertical blue line? Well, we have y1 to y2 is the distance from y1 to y2. And again, if y1 were 3 and y2 were 7, what's the distance between 3 and 7? Well, 3, 4, 5, 6, 7, it's 4, right? So this is y2 minus y1. Okay. at least in the picture that I've drawn, where x2 is bigger than x1, y2 is bigger than y1. All right, now why do I care about that? Well, the length that we actually want is the length of the hypotenuse of this triangle, and we know from the Pythagorean theorem what the length is, right? So it's equal to distance, or length of that segment, I guess I've been calling it distance, is equal to distance squared. Let me just write it down with the Pythagorean theorem. Distance squared that we want, right? This is the guy that we want, question mark, is equal to, its square is equal to x2 minus x1 squared plus y2 minus y1 squared. Okay? And so the distance that we actually want is equal to square root of that. All right, so this is the distance formula for the distance between 2 points. Okay. Again, technically, I should have popped out a plus or minus here, but since we're talking about actual physical distance, it can't be negative. So I've kind of glossed that over and just used the positive square root. All right. Okay. So this is super useful. We'll be calculating with distances a lot in this class, and this is where that distance formula comes from. Now that you know where we got it from, you don't actually have to memorize it, because you can always reproduce the formula as you need it from this picture up here. Okay. Let's see. So a few notes about this distance formula. Notice that this thing is a plus as opposed to a minus, whereas these two guys are minuses, right? So if you're memorizing this guy, it's very easy to kind of misremember which ones are pluses, which ones are minuses, or how it works. One way you know whether you have it right or not is that if this plus in the middle were a negative sign, then it's possible that you would have a negative square root, right? Because anytime you subtract things, it's possible you get a negative number. And then that would mean you have a negative under the square root. But how could you have, it doesn't make sense, right? To have 2 points whose distance between them is a square root of a negative number. That makes no sense. Okay, so you know that this guy in between has to be a plus. Now, why can these guys in the middle, these two guys on the sides, right, this x2 minus x1 and y2 minus y1, why can they be negatives? Doesn't that cause a problem? Well, it doesn't, because you're squaring the number, right? So whether x2 minus x1 is positive or negative, you're squaring it. So no matter what, this guy on the left is actually going to be positive. And no matter what, this guy on the right is going to be positive. So there's no worry about having a negative under the square root due to these two negative signs. All right. Note another thing, that I chose to write this as x2 minus x1 and y2 minus y1, but it doesn't matter. I could have written it as x1 minus x2 or y1 minus y2. Doesn't matter, because ultimately the difference between x2 minus x1 and x1 minus x2 is a minus sign, right? 7 minus 3 is 4, and 3 minus 7 is negative 4. But no matter what, I'm going to be squaring the number. So whether it's 4 or negative 4, I'm going to square that. I'm going to get 16. All right. So the order in here, x2 minus x1 or x1 minus x2, doesn't matter at all. Okay. So from this, we can talk about a whole bunch of other quantities. Now that we can, we understand the concept of the distance between 2 points, or the length of a line segment, we can talk about things like midpoints, right? So if I have x1, y1, and I have x2, y2, right? What's the midpoint? Where's the midpoint, right? Where's the point that's equally far from the point on the left and the point on the right? So that's asking, what's the point whose distance to x1, y1 is equal to its distance to x2, y2? All right. So if you want to solve this, this is solving an algebra problem, right? Right. I just said the word equals, right? So what you would do is you would write this as x comma y. That would be your unknown point, right? You would want the distance, and so that means write down a distance formula, right? So that that means we would need distance from our point to x1 comma y1, so x minus x1 squared plus y minus y1 squared, right? Square root, that should be equal to its distance from to x2. Distance, to x2 comma y2, all right? And that gives you the midpoint. Okay, of course, we're demanding that the point actually be on this line segment, right? So need x, y on line segment. Now, there's an issue here. This is kind of complicated, right? We got square roots, we got squares. It's kind of a mess, right? So there's actually a shortcut here to remember how to understand the midpoint of a line segment. And that's actually, the answer is x1 plus x2 over 2, comma y1 plus y2 over 2. All right. How do I know this? Well, if you think about the midpoint, right, in terms of, let me draw a picture again down here. x1, y1, x2, y2, right? We're looking for this midpoint. The midpoint here should be halfway in terms of the x, right, distance, the horizontal distance, and it should be halfway in terms of the y distance, the vertical distance, right? And so essentially what you're doing is you're calculating with these two quantities that I've written down, x1 plus x2 over 2 and y1 plus y2 over 2 is the average. So this guy here on the left is the average x value, and this guy here is the average y value. All right. So the midpoint is in a way the average of the 2 points. All right. And again, these are the averages because when you have two numbers, when you add them and you divide by 2, that's the average of the two numbers, right? So essentially, perhaps the right way to remember this is the midpoint is the average of the x coordinates, comma, the average of the y coordinates. Okay. And why does it make sense that is the average? Well, if x1 is here, x2 is here, what's the entire length? The entire length is x2 minus x1, right? And so what exactly is the coordinate right there? Well, it's halfway, right? So that coordinate is distance to x1 is x2 minus x1 over 2, halfway, right? So what is actually the coordinate of that point? Well, x1 is not at 0, so here's 0. So if this distance here is x2 minus x1 over 2, and that distance here is x1, then altogether, the distance from here to there is the sum of them, x1 plus x2 minus x1 over 2. And that's x1 plus x2 over 2 minus x1 over 2, which is x1 over 2 plus x2 over 2, if you simplify it. And that's exactly what I said in terms of the average. Okay, so that's if you really want to go down and very carefully figure out exactly the coordinates. Okay, so that's the midpoint between 2 points. If you go on to take more math, you'll see this concept of averaging quite a bit. When you talk about center of mass of an object, that's basically essentially the same idea. You're taking the average in a way of x coordinates versus average of y coordinates, except you're doing, instead of just adding things, you'll be doing very complicated calculus things instead. But the concept is roughly the same. Okay, so that's one minor application of our distance, the idea of the distance. But a really important application was circles, is circles. So let's talk about a circle. So let me draw a picture first. We got a circle, let's say of radius 3, about 4, 5. All right, so 1, 2, 3, 4, 1, 2, 3, 4, 5. So here's our center. It has radius 3. Okay. 4, 5. Okay. So how do we describe this guy mathematically? How do we write down an equation for this circle, right? I mean, it's good to be able to draw a circle and kind of see a picture, but if you actually need to do computations or you need to solve problems involving the circle, pictures are very frequently not going to help you. And in fact, they're frequently going to be very misleading because sometimes you just don't draw an accurate picture that's perfectly round or whatever, right? So this circle that I've drawn is not perfectly round. So if you really want to do computations that are correct, you better work with actual algebra as opposed to pictures. So what it would be the formula for this circle? Well, if we think about what a circle is, we can just pop it right out naturally using the idea of the distance between 2 points, which again boils down to the Pythagorean theorem. All right. So what is a circle? Well, circle of radius 3, about 4, 5, right? So let's say x, y is on this circle. So this statement here, x, y is on this circle. That's equivalent to saying x, y is a distance of 3 from 4, 5. All right, so this is actually the key point. Okay, to be on the circle means you're the distance of r, whatever the radius is, 3, from the center. Okay, so here, in terms of our picture, every point that's on this circle here, its distance to our center is 3. All right, every point that's not on the circle, its distance to the center is either bigger than 3 or less than 3. All right, but not equal to 3. All right, so to be on the circle means you have a distance of, in this case, 3 from the center, 4, 5. All right, now this is the key point because I know what the distance is, right? I know distance formula. So what does that mean? X, y is a distance of 3 from 4, 5 literally means x minus 4 squared plus y minus 5 squared, square root, that's the distance, right? Let me put this in quotes. Distance from x, y to 4, 5. All right. Distance of 3, so is equal to 3. All right. So here we can see this equivalence idea, right? To be on the circle is the same as this quantity is equal to 3. All right. Now, like I said, this thing on the left-hand side is positive. The stuff inside the square root is positive because it's a sum of 2 positive things. And so oftentimes we're not necessarily comfortable with square roots. So I'm just going to square both sides so that I don't have to look at square roots, right? So this is the same as x minus 4 squared plus y minus 5 squared equals 3 squared. Okay? And this is the traditional form of the equation of a circle. All right? And again, we've derived this formula from the distance formula, directly from the idea of the distance formula. And that, again, was from the Pythagorean theorem. All right, in terms of recognizing the features of this circle from the formula, that 3 squared, that's our radius squared. Let me emphasize that, oops. This entire right-hand side, let me just put a box here. This guy here is the radius squared, right? And then here's our center, 4, 5. Okay. So for example, if I wrote down x plus 3 squared minus plus y minus 5 squared equals 64, then this would be a circle, radius of square root 64, which is 8. Okay. And again, we don't have to worry about -8 because we're talking about actual physical circles here. And its center is -3, 5. Okay, because here the negative sign, right, -4 meant the circle had center 4, comma, -5 meant it had center 5. So in a way, the right way to think of this x plus 3 is it's x minus -3 squared, all right? And so this thing, x minus whatever that thing is the center, is the x-coordinate center. So -3. And then here, y minus the coordinate of the center, 5. Okay? All right, so that's how you would pick out the radius and center of a circle. Okay. So on the homework, what you'll see is problems where they want you to write down the equation of a circle given certain bits of information. The key thing to remember, even for the easy ones and for the hard ones, is that what you need for a circle, equation of a circle, you need two things, right? For the equation of a circle, you need one, you need the center, and two, you need the radius. And as long as you have these two bits of information, you can just use our procedure above or just memorize the formula, and you've got the center. And you've got the equation. All right, so there'll be problems on the homework where it doesn't explicitly give you the center, it doesn't explicitly give you the radius, but you need to kind of look at the geometry of the picture to figure those two guys out. But once you figure those two guys out, you're all set. Okay. All right, so that's the that would be the online homework I'm talking about. So for this week, generally, our paper homework will be also exactly what we talk about here, and will be related to the online homework. But the exception is this week, week 1, where I've put a different style of paper homework. Just to show you that kind of the point is to say that you want to write up your work nice and neat, and you want to also evaluate your answers, especially to physical type of problems, to see if they make sense. All right. So the paper homework is about grading some problems in a way, and you'll see some terrible mistakes perhaps, and hopefully you'll try to avoid the same kind of mistakes you see on the paper homework. All right, but again, generally our paper homework, our online homework, and our lectures will be very closely related to each other.